Pluto sits 3.67 billion miles from Earth. At that distance, a radio signal traveling at the speed of light takes more than 5 hours to make a single trip. No human has ever set foot anywhere near it. Exactly one spacecraft has ever flown past it for a matter of hours before continuing on into the dark and never coming back. For nearly a century, scientists simply accepted that Pluto would stay one of the great unsolved mysteries of our solar system, because the technology needed to actually study it did not exist. Then James Webb turned its mirrors toward that frozen, distant world, and what it found broke the room. The lead researcher on the study stood in front of his colleagues, looked at the data, and said 4 words that stopped every conversation cold. "This is unique. Not rare, not unusual. Unique. In every recorded observation of every planet, moon, and object humanity has ever studied. Nothing works the way Pluto works." And that was only the first discovery, because by July of 2026, James Webb had found something else, sitting quietly on Pluto's surface, that also appears on one other world in the solar system and matches absolutely nothing in the entire catalog of known chemistry. Scientists still cannot identify it. Stay with me, because this is the full story of what James Webb actually saw at the edge of the solar system, and why a frozen dwarf planet, dismissed for decades as an afterthought, may be quietly holding answers to one of the oldest questions in science: how life began at all. To understand why this discovery matters so much, you need to understand how little we actually knew about Pluto before Webb arrived. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at Lowell Observatory in Arizona, using nothing more than photographic plates and a keen eye for a tiny point of light that had shifted position between nights. For 76 years, Pluto held the title of the 9th planet. Then in 2006, the International Astronomical Union redrew the definition of a planet, and Pluto was reclassified as a dwarf planet, a decision that sparked more public outrage than almost any scientific ruling in modern memory, and one that is still argued over today. But the classification debate was never really the point. The real question was always what Pluto actually is, what is happening on that surface, what its atmosphere looks like, whether it is a dead frozen relic, unchanged since the birth of the solar system, or something far stranger. And for most of the century since its discovery, nobody could answer that, because Pluto is too small, too dark, and too far away for any telescope on or near Earth to resolve in meaningful detail. Even Hubble, the most celebrated telescope of the 20th century, could only produce blurry, pixelated smears where Pluto's surface should be. Everything changed on July 14th, 2015. After more than 9 years crossing the solar system, NASA's New Horizons spacecraft made its closest approach, passing within 7,800 miles of Pluto's surface and sending back data that rewrote the textbooks overnight. What it found was not a dead rock. It found a world of staggering complexity. Nitrogen ice plains so smooth and young, they had to be geologically active, somehow constantly renewed this far from the sun. Mountains of water ice rising nearly 2 miles into the black sky. A massive, bright, heart-shaped basin, now known as Sputnik Planitia, instantly one of the most recognizable features in the outer solar system. And an atmosphere, thin and layered, wrapped in a blue haze that scattered sunlight in a way that gave Pluto's skies the same color as Earth's. New Horizons proved beyond doubt that Pluto was alive in a geological sense, doing things no model of a small icy world had ever predicted. But New Horizons was a flyby. Hours of close observation, not months or years. And its instruments, brilliant for a mission designed in the 1990s, had one critical blind spot: the mid-infrared. That is the exact part of the spectrum where Pluto's true atmospheric chemistry hides, revealing heat signatures and molecular fingerprints that visible light simply cannot show. No instrument sensitive enough to read those signatures at Pluto's distance had ever been built, so scientists did the only thing they could. They wrote papers about what they expected to find, built theoretical models, and waited for a telescope that did not yet exist. Then James Webb arrived, and its MIRI instrument finally opened that unexplored window. The results were published in back-to-back papers in April and June of 2025. led by an international team from the CNRS Paris Observatory and the University of Reims-Champagne-Ardenne. And to understand why what they found is so extraordinary, you need to understand why the mid-infrared matters so much in the first place. Infrared astronomy is, at its core, the study of heat. Every object radiates infrared light based on its temperature, and every molecule absorbs and emits that light at its own unique wavelength, like a chemical fingerprint. Read those fingerprints correctly, and you can identify the exact compounds sitting on a surface or drifting through an atmosphere billions of miles away. The mid-infrared range, roughly 5 to 27 micrometers, is especially rich for the organic chemistry and icy compounds scientists expected at Pluto. But detecting a signal that faint from something that cold and that far away requires sensitivity that borders on impossible to engineer. James Webb achieved it, and what came back matched nothing in the existing models. Back in 2017, a planetary scientist named Shi Zhang at the University of California, Santa Cruz, published a hypothesis that most of his colleagues treated as an interesting long shot. He proposed that Pluto's atmosphere was not primarily controlled by its gases, the nitrogen, methane, and carbon monoxide that make up the bulk of what is there, but by haze, tiny organic particles suspended high above the surface, absorbing sunlight and radiating it back out as heat, functioning as a kind of planetary thermostat. He predicted that if this haze theory was correct, it should be emitting strong mid-infrared radiation detectable by a sufficiently sensitive telescope. Nobody could test the idea in 2017. The telescope that could test it simply did not exist. When James Webb's data was finally analyzed in 2025, it confirmed Zhang's prediction completely. Pluto's atmosphere is filled with haze particles that heat and cool in cycles, and those particles, not the gases, control the entire energy balance of the atmosphere. The lead researcher on the study, Tanguy Bertrand of the Paris Observatory, put it as plainly as a scientist ever will. This is unique in the solar system. Every other atmosphere ever studied on any planet, any moon, anywhere, is regulated primarily by its gases. Pluto is regulated by its haze, a layer of microscopic, solid organic particles floating in the upper atmosphere is doing what nitrogen does for Earth, what carbon dioxide does for Mars, what ammonia does for Jupiter. It is the thermostat. It is the dominant force controlling the entire climate of the planet, and nothing like it has ever been found anywhere else in the solar system. That haze is cooling Pluto's upper atmosphere by roughly 30 degrees Celsius, far more than any previous model predicted, on a world already sitting at around minus 230 degrees Celsius. That means every atmospheric model ever built for Pluto was fundamentally wrong, not about the chemistry, but about what was actually driving the system. The true engine of Pluto's climate was completely invisible to every instrument that had ever studied it, until now. But the haze discovery was only the first layer, because while it cools Pluto's upper atmosphere, that same haze is doing something else with absolutely no parallel anywhere in the solar system. It is energizing methane and other organic molecules at the outer edge of Pluto's atmosphere and kicking them out into space. And some of those escaping molecules are being captured by Charon, Pluto's enormous companion moon, and slowly settling onto its poles. Charon is stealing Pluto's atmosphere, not in one dramatic event, but continuously, silently, molecule by molecule, across billions of years. The strange dark reddish stains on Charon's polar regions, the ones that puzzled scientists when New Horizons first photographed them in 2015, are Pluto's own material. Organic molecules that escaped, drifted across the void separating the two worlds, landed on Charon's poles, and were then cooked by solar and cosmic radiation into complex reddish organic compounds called tholins. What looks like a simple surface feature on Charon is actually a physical record of billions of years of atmospheric theft between two neighboring worlds. Nothing like this relationship exists anywhere else that we have studied. Not just two bodies orbiting each other, but two worlds locked in a slow, continuous chemical exchange across open space. James Webb's instruments took that story even further. Using its near-infrared spectrograph, researchers detected carbon dioxide and hydrogen peroxide on Charon's surface, alongside ammonia and crystalline water ice. hydrogen peroxide matters enormously here because it forms when radiation interacts directly with water ice, which means active surface chemistry is happening on Charon right now in real time. Active chemistry on a moon more than 3.5 billion miles from the sun with no internal heat, no liquid water, and no atmosphere of its own. Cosmic radiation is continuously reworking the material on Charon's surface. The base layer of water ice, the organic compounds arriving from Pluto, all of it being transformed into new molecules that were not there before. Charon is not a dead rock. It is a slow-motion chemistry lab running purely on cosmic radiation, quietly manufacturing new compounds in total cold and total darkness at the far edge of the solar system. If a story like this is the reason you watch space content in the first place, take 2 seconds and hit that like button right now. It genuinely helps this channel keep making deep dives like this one, and I want you here for what comes next, because it gets stranger. Webb's spectral study of Pluto itself, across a wavelength range from 4.9 to 27 micrometers that had never been explored before due to instrument limitations, revealed a level of chemical richness nobody expected. Signatures of methane ice, deuterated methane, ethylene ice, and detailed thermal emission patterns from the haze that gave scientists a picture of the atmosphere's structure and composition unlike anything captured before. And then, in July of 2026, came a discovery that stopped researchers cold. While analyzing Webb data from Titan, Saturn's largest moon, using both the near-infrared spectrograph and the MIRI instrument, scientists found an unexpected absorption feature centered at exactly 5.113 micrometers. At that precise point in the spectrum, Titan's surface was absorbing light in a way that matched nothing on record. The team compared the signal against every known atmospheric gas, every known haze particle, every known ice and organic compound in the scientific literature. Nothing matched, nothing. An unidentified substance on one of the most heavily studied moons in the entire solar system. Titan is not some obscure, poorly understood world. It has been visited by the Cassini spacecraft, studied for decades, and sits at the center of modern astrobiology because of its thick nitrogen atmosphere and its lakes of liquid methane. And even there, Webb found a signature current chemistry cannot explain. Then the researchers went back and checked Webb's earlier Pluto observations from May 2023. And there it was, the exact same absorption feature at 5.113 micrometers on Pluto's surface. The same unidentified fingerprint showing up on two completely different worlds billions of miles apart. The depth of the absorption was almost identical on both, somewhere between 4 and 7%. But the width of the feature on Pluto was roughly 3 times broader than on Titan. Same molecular signature, different shape, and that difference is not a source of confusion, it is a clue. It tells researchers something about how this unknown compound behaves differently under each world's specific surface conditions. Titan has a thick atmosphere and liquid methane lakes. Pluto has a thin haze atmosphere and nitrogen ice plains. The fact that the same substance appears on both under such different environments suggests it forms through some shared chemical pathway that operates broadly across the outer solar system, rather than something that needs one very specific local condition to exist. Scientists are now running laboratory experiments back on Earth, testing whether candidate molecules mixed and altered to mimic Titan and Pluto surface conditions can reproduce this exact spectral fingerprint. Researchers also want to map where the substance sits on Titan's surface to see whether it correlates with known geological features like the massive dune fields that stretch across Titan's equator. If the mystery compound concentrates in the dunes, that tells you one story about how it forms. If it is spread evenly across the surface, that tells you a completely different one. NASA's Dragonfly mission, a nuclear-powered rotorcraft built to fly directly through Titan's thick atmosphere and land at multiple sites, is scheduled to launch in 2028 and arrive at Titan in 2034. When it lands, it will be able to sample this substance directly and finally identify it in a lab. But that answer is still 8 years away. For now, an unidentified molecule sits on the surface of at least 2 worlds in our solar system, and modern science simply cannot tell you what it is. Step back for a moment and take in the full scope of what all of this means together. Pluto completes one orbit around the Sun every 248 Earth years, which means Webb's observations from 2022 through 2025 are only capturing the very earliest stages of a long Arctic winter descending on Pluto's north pole as it drifts further from the Sun. Scientists expect the haze thermostat to work even harder as sunlight fades from Pluto's perspective, and Webb is positioned to test that prediction across the next decade. This is a genuinely historic moment because for the first time since Pluto's discovery, there is an instrument capable of watching it change in something close to real time. Not on geological timescales spanning centuries, but year over year on the timescale of a single working space telescope mission. Webb can return to Pluto every observing season and directly measure how its atmosphere shifts as the planet moves along its orbit, testing the physics of its climate against real predictions and refining our understanding of how haze-dominated atmospheres actually work. And the implications reach far beyond Pluto itself. The same radiative haze physics discovered here could be shaping other thin nitrogen and methane-rich atmospheres across the solar system, including Triton, Neptune's largest moon, the upper layers of Titan's atmosphere above its thick lower layers, and potentially atmospheres on planets orbiting other stars entirely. Pluto has effectively become the first natural benchmark for an entire category of atmospheric physics: exoplanets. This is exactly where a frozen dwarf planet, billions of miles from Earth, connects directly to the cutting edge of modern astronomy. One of the hardest problems in characterizing distant exoplanet atmospheres is interpreting haze signatures, because until now, every model of how haze behaves was built purely on theory and laboratory guesswork. Pluto is now the first real natural laboratory where haze is the dominant atmospheric force, observable with the exact same telescope currently being used to study exoplanets, allowing for direct comparison and model validation that was simply impossible before this discovery. And then there is the connection that matters most. Before oxygen transformed Earth's atmosphere roughly 2.4 billion years ago, our planet was wrapped in a haze of organic particles, nitrogen and hydrocarbon chemistry strikingly similar to what exists on Pluto right now. That ancient haze may have helped stabilize early Earth's temperature and created the exact conditions that allowed life to eventually take hold. Studying Pluto's haze today may hand scientists new insight into the conditions that made Earth habitable in the first place. The lead scientist on the haze study said this directly, not as speculation, but as genuine scientific motivation. Understanding what is happening in Pluto's atmosphere right now may help answer one of the oldest questions science has ever asked. How did life actually get started on Earth? This is the full arc of what James Webb has revealed at Pluto. A world that was nothing but a blurry point of light for most of human history. A world that got one brief close-up from a spacecraft that flew past once and kept moving. A world stripped of its planetary title and dismissed by pop culture as an afterthought. A world that, the moment the right instrument finally looked, turned out to host a climate system found nowhere else in the solar system. An atmospheric haze acting as a planetary thermostat with no known parallel. A companion moon continuously fed molecules stolen from its neighbor's atmosphere. Active radiation chemistry running right now in the cold and the dark. An unidentified substance on its surface that also exists on Titan and matches nothing in the known catalog of chemistry. And a direct line connecting all of it to the exact conditions that may have allowed life to begin on Earth. If this is the kind of story that genuinely rewires how you think about our own solar system, subscribe to this channel and turn on notifications right now